Okay, so here's the challenge laid out for us. We've got 3 columns, and right away you can see they're carrying very different loads. We're talking 800, 1280, and 960 kilonewtons. And to make it trickier, they're not even spaced out evenly. Our job is to support all of this weight on one continuous piece of concrete.
So, yeah, that's the big question, right? How in the world do you design one foundation that can handle these huge, unbalanced forces without tilting or cracking or, failing? That's exactly what we're going to figure out one step at a time.
First things first, we've got to lay the groundwork, pun intended. Before we can even think about doing any calculations, we need to get a handle on the basic ideas and the materials we're going to be working with.
And the solution to our problem is something called a combined footing. The easiest way to think about it is like a big concrete raft. So instead of giving each column its own little concrete shoe, we build one giant slab that connects them all. And the real genius here is that it takes all that intense pressure from the columns and just spreads it out over a much, much larger area. That way, the soil underneath can handle the weight, no problem.
And here are the rules of the game. We've got the soil's capacity, that's how much of a beating it can take. We've got the strength of our concrete, and, really important, the strength of the steel rebar we're going to put inside it. Basically, these numbers set the limits for our entire design. We can't break these rules.
All right, let's get into the first big step. We need to figure out the exact size and shape of our footing. And this is all about finding the perfect balance. Think about it like a seesaw, but with 3 people on it, and they all weigh different amounts. To keep that thing perfectly level, the pivot point can't just be in the middle of the board, right? It has to be at the exact center of gravity of all that weight. Well, our footing is the seesaw, and our goal is to find that perfect balance point for our column loads so that the pressure on the ground underneath is totally even.
And now, the math. I know, this looks a little intimidating, but the logic behind it is actually pretty simple. All we're doing is finding that center of gravity. We're basically taking each column's load, multiplying it by its distance from the edge, and adding it all up. The result, that little x, tells us the precise spot where the total load, all 30-40 kilonewtons of it, is perfectly centered.
So, what does all that math get us? It tells us that for the ground to push up perfectly against the columns pushing down, our footing needs to be exactly 11.3 meters long. That length is the magic number that lines everything up.
Okay, so we've got the length, now we need the width. And this part's actually a lot simpler. We just take our total force, that 30-40 kilonewtons, and divide it by how much pressure the soil can take. That gives us the total area we need. Then, we just divide that area by our length, 11.3 meters, and bam, we get a width of 1.8 meters.
And there you have it. That's the result of our first big step. Our final footprint is 11.3 meters long by 1.8 meters wide. It's now perfectly sized and positioned to keep everything in balance. The footprint is set. But is it thick enough? You see, having the right size footprint is only half the story. Now we've got to make sure those columns don't just, punch a hole right through our concrete slab. And that risk has a name. It's called punching shear. A really simple way to picture it is to imagine pushing your thumb hard through a piece of cardboard. That's exactly what a heavy column wants to do to the footing. Our job is to make sure our concrete is thick enough and strong enough to stop that punch. So the whole point of this check is pretty simple. We figure out the punching force the column is dishing out, and then we figure out the concrete's ability to resist it. And at the end of the day, the resistance has to be a lot bigger than the force. Simple as that.
So here's the actual engineering check for that middle column, which is the heaviest one. Now, don't get bogged down trying to decode all the symbols in these formulas. The only thing that really matters is the comparison at the very end. Is the force pushing up, Vu, less than the concrete strength, phi Vc? And the results are in. The force acting on the footing is a little over 1,450 kilonewtons. But the concrete's resistance, at a thickness of 700 millimeters, is over 3,200. So our resistance is more than double the force. That's not just a pass, that's a great pass. Our footing is definitely thick enough.
Okay, so our footing has the right size, and we know it has the right thickness, but we're not done yet, not even close. Now we need to look inside the concrete itself. We have to map out all the hidden stress points to figure out exactly where the steel reinforcement needs to go.
Because even though the footing just looks like a boring, static slab of concrete, it's actually alive with all these internal forces. It's being pulled and pushed and bent all over the place. So the question is, where are these invisible forces the strongest? That's what we need to know.
And here's our answer. You should think of these diagrams as an X-ray of the footing. They let us see all those hidden stresses we were just talking about.
And this map, showing the shear force and the bending moment, is probably the single most important thing an engineer uses to know exactly where the steel needs to go. So let's just quickly break this down. The middle diagram shows shear. Think of that as a vertical slicing force. The bottom one shows the bending moment. That's where the footing really wants to bend and crack. And here's the key. Just look for the peaks. The highest and lowest points on these graphs are the hot spots, the points of maximum stress. This is literally a treasure map that tells us exactly where to put our steel to make the whole thing strong.
All right, let's pull all this together. We've gone all the way from a tricky problem with 3 columns to a full-on plan for a safe, stable foundation.
You know, we've followed a really clear, logical process here. We started with the problem, figured out the loads. Then we sized the footprint to get the balance just right. After that, we made sure it was thick enough to prevent that punching shear. And finally, we created this detailed map of all the internal forces. Every step just builds on the one before it.
And that quote really nails it, doesn't it? That's what this is all about. Taking a simple problem, analyzing all the forces, the ones you can see and the ones you can't, and creating a detailed, calculated blueprint that guarantees safety. So we've done all the hard work of finding out where the stresses are. But that just leads us to the next huge question. Exactly how much steel rebar do we need to put in those high-stress spots to fight back against those bending and shear forces? Well, that's the final piece of the puzzle.